I want to give you a quick idea of what we're going to be doing this semester in Calculus 2. Calculus 2 is integral calculus, so we're going to be focusing on integrals the entire semester. In Calculus 1, you learned how to take antiderivatives and calculate integrals. You learned how to handle straight line motion pretty well. That was your main application most likely. So if you can take derivatives, you can go from position to velocity to acceleration by taking rates of change. And then if you can take antiderivatives, you can go in the opposite direction from acceleration to velocity to position. And so you can analyze that pretty well using those tools. As people started to try to use those tools on a wider variety of applications, they started coming across different functions. So the first thing that we're going to do in this class is look at more applications. So we're going to extend your base of applications. Then the second thing is we're going to look at different functions that come up naturally in those different applications. Integrating those new functions will require some new techniques. So we'll spend some time doing that. And you already know how to find antiderivatives for some really simple functions, but there's a lot more out there than just the simple ones that you already know how to do. Then at the end of the semester, so maybe like the last third of the semester, we're going to get into something that's really pretty mind-blowing, how powerful it is and useful. It's something called series, infinite series. And the idea is, if you're working on applications, you need to make measurements and get approximations in these real-world problems. And sometimes you can't even find an antiderivative for a given function. There's just no known way how to do it. So you can use these approximations to do it even for those unknown functions, the functions with unknown antiderivatives. And what you do is you take a function like something like e to the x, and you rewrite it in really simple pieces, starting with a constant term, so just a number, plus, and then a constant times x, a linear piece, and then plus a quadratic piece, so a constant times x squared, plus a cubic piece, constant times x cubed, plus, and you just keep going following that pattern, getting higher and higher powers of x. And you can rewrite functions as this infinite sum or this infinite series of terms like that, polynomial terms. So you can take antiderivatives of those polynomial terms really easily using just the power rule. And this allows for much more powerful applications than what you could do without these. These infinite series behave a little wildly because you're adding up infinitely many terms, and so they were used to do a lot of really amazing things when they were discovered, but they also caused a lot of confusion for like 100 years. We're not going to get into the details of how people ironed out how everything works when you're adding up infinitely many things. For us, we're actually mostly going to be taking a finite number of terms and then chopping off the rest of it, because what happens is you have some degree of accuracy that you need, and you just include as many terms as you need to get to that degree of accuracy, and then you don't worry about the rest. You don't worry about making it completely perfect, because each term that you add on, the linear piece, the quadratic piece, the cubic piece, and so on, each piece gives you a little more accuracy in your calculations. So once you get as far as you need, cut the rest off. That's basically what we're going to be doing this semester. It's challenging, it's powerful. I hope you enjoy it.